real exam questions. This is question 29. It's about slab design with the use of yield lines. Prove that the yield line of an isostatic slab bearing in one direction lies in the center of the span. So you have a slab going from this side to this side, no support on the shorter side. In direction of L, there is no support, and in B, it's simply supported. This is our slab under consideration. So we look at the section through here, an horizontal section, and you see this is simply supported, uniform distributed load over the distance L, a span L. Dealing with yield lines, we look up the axis of rotation, which is of course at the supports, and here too. But now we have to find a yield line, and the yield line starts at the crossing of two rotation axes. So this means, because those two are parallel to each other, that this point is at distance infinity, or it means it must be parallel to those two axis lines too. So that means that the yield line is a straight line like this, but we do not know its position. It lies on a position alpha L, and then of course the other side is 1 of L minus alpha L. So that's what we are now, our parameter is alpha, and we will optimize alpha in such a way that we have the maximum bending moment. The angle of rotation here is theta. We assume, of course, that theta is small in such a case that the tangents of theta can then be replaced by delta divided by the distance to the support. So we have the slab. We know that the work done by the external forces must be equal to the work done by the internal forces, or you can write it in this simplified formula. The work done by the external forces is then, for this slab, the total load on this portion of the slab, which is Q times B, and the length, times alpha L, this is alpha L, and the mean deflection of this is delta, then the mean deflection is, because it's a rectangular, delta over 2. Then we take the other part, it's also B times Q, the total load, times 1 min alpha L, and also the mean deflection is delta over 2. Of course, we could have seen that from the beginning, that the work done by the external forces, it's the total load divided by delta, divided by 2, because it's rectangular sections. The work done by the internal forces is the bending moment projected on the axis of rotation here. The length then is B times the bending moment M times the angle of rotation, which is delta, divided by alpha L. And we do the same for the other side. Again, it is M projected on this axis of rotation, which is B, and the angle of rotation is delta divided by 1 min alpha L. We can simplify it to this equation. Now we know E must be equal to D. So there, and then we can get from this equation M, which is expressed like this. So it's a function of alpha. Now the question is, for which alpha is M now maximum, extreme? We take the first derivative and put it equal to 0. Then you get this as an expression, and from that you get alpha. This is 0 when alpha is 0.5. So this proves that the yield line lies in the middle of the span, leads to maximum bending moment.